All right, so these are a few of the dates. So every day I'm going to post kind of what we did for the day, and I'll post what we're going to do for like on the next day, just to make sure that you guys know the schedule and everything that's going on, because I know that there's a lot of stuff going on. This week, this is probably the only class that you guys have. I don't know if other instructors started, but I know that probably most of them have not. So it might be fine for this week. You might be saying that wasn't so bad, but then next week, when you all of a sudden have every one of your classes going, there's going to be a lot going on. So that's why I'm going to make sure that every day, or at least on the days that we meet, I will write anything that is due or what we're going to do on the following day. So yesterday I posted that on 3/25, which is now, we will continue to do an exam review, which is now, remember, next Tuesday on the 31st. Let me just double check that's correct. Yes, that is correct. All right. And then class will now be on Tuesdays and Wednesdays. And then on Thursday, it will be more of an open class question and answer, or office hours or anything else. As you can imagine, the staff and the faculty are having a lot of meetings this week. So tomorrow, we're going to have to cut it early in that class, because I have a meeting, I think, at like 10:45. I'm sorry, at 11:45. I think for this week, there's a lot of the meetings, since technically the faculty aren't supposed to be back. But we'll get back on the schedule. Hopefully, this is kind of a good schedule, and it works out. As far as your homeworks, your quizzes, those will still be due midnight at 9 o'clock. So Chapter 7 homework will be due next Monday at midnight, okay, or 11:59, how we have it. So that is Monday evening going into Tuesday. So exactly how we've been doing it in the past. So that's for Chapter 7. And then your exam will be on the very next day. All right, so this is next Monday. And then I've also activated all the pre-labs, and I'll show you all this just to kind of show you. So I've activated all the pre-labs, and they are to be due Monday the 4th, or May 4th, by midnight. May the 4th be with you. Is that Star Wars Day? National Star Wars Day. May 4th is right here, so it's Monday by midnight. I believe our last day of class is on that Thursday. Okay, so I believe that Thursday, the 7th, is the last day. So I just made all those pre-labs due on the very last day. You just confirm there's no quiz for 7. That's correct. There's no quiz for Chapter 7. Correct. Yep. Yeah. It's only for Chapter 7, because those quiz questions really weren't that good. I didn't really like them. I don't think it helped out. I think it would hinder more than it helped. But the homework is still there, still posted. And then the virtual labs I talked about, I'll post those as soon as I can. Though I told you guys about a super code that we got from the publisher. They do not seem to be working at the moment, so we have to figure that out. But there is no rush, because I think we have, 8 weeks left, or 7 weeks, so there really is no rush. I will get those posted as soon as they are activated. I'm sure McGraw-Hill is pretty busy as well. Those have not been activated, however, all the pre-labs have. Okay, so let me just kind of show you everything. Also in assignments, I've noticed that a few people I actually have an assignment waiting there now. So there are 2 assignments, so you guys are doing good on the Dropbox, or at least the 2 people that have done it. I have gotten those, so great, thank you very much. That seems to be working. The quizzes I've activated just to show you. I've activated all these pre-lab quizzes, so these should be all activated. They're all due, as May 4th by 11:59 p.m. So the gas law, so I'll let you guys, I'll figure out when you want to do them. If you want to do them all this week, if you want to do one a week, since we've already talked about the gas laws, it's kind of fresh in your memory, but for sure by next Wednesday, after the exam on Tuesday, on Wednesday, we'll kind of go over that again, just to kind of review. All right, and then acid-base indicators and the reactions, if you want it. And again, they kind of follow along with lecture. Now that we aren't forced on a certain day in order to do them, we can actually wait a little bit longer after a lecture is done, and then you can actually do them. Because I believe one of these, I think the chemical reaction lab, when we actually do it in class, it's a week prior of the lecture. So you don't really learn the stuff yet. You kind of learn it in lab quickly, and then we talk about it. So if you want to wait till after our lecture and do it, that would probably be better. Okay, so I posted all those. There are 6, I believe. 1, 2, 3, 4, 5, 6. Okay, and what I'll do is these are not auto-graded, so it'll grade you, but it doesn't update it in the in our grade book. So at the end of every week is probably when I'll be able to update everything. Okay, so if you take it like on a Monday, it might not show up in the grade book till like Friday or Saturday until after I get to it and I post it in there. Okay, so I just want to let you know that when you take it, it doesn't automatically update it. I think other than that, I hope yesterday it was good for everybody. It kind of got us back to normalcy, and hopefully you guys feel better about how the class is handled and how we'll finish it. And I think, like I said yesterday, even though officially we're not, this is only supposed to be for a few weeks, I really think it's going to be for the semester. Okay, I think other than that. Okay, good. Thank you, Jordan. Okay, oh yeah, so I wanted to show you this, the exam prep. You guys already knew about this, but just, I'm going to pull this up so that we have this available. So this is just all the topics that we've talked about that you need to know for the exam. So yesterday we did all of Chapter 5, so all the concepts of the mole, understanding what it is and what Avogadro's number tells us, conversions from moles to grams, the number of moles to atoms, so using Avogadro's number, so that's that little chart that I keep showing you guys. And then knowing what the atomic mass and a molecular mass is and how to find those, what molar mass implies, so that's basically the mass of 1 mole, all right, pretty straightforward. And mole-to-mole conversions and how to use them in calculations, so going from moles to grams, the number of molecules, and then if I give you, moles or grams of one thing, you know how to convert it into moles of another thing. Mass percent composition, so we did a problem like that yesterday with the carbon monoxide problem we did with that, and then doing the empirical formula and a molecular formula in those calculations, all right? So that is what we did yesterday. So today, the plan is to just go over Chapter 6 and 7, just kind of review those, do a few problems, and then take any questions that you guys have. And again, if you guys feel more comfortable in typing it in, that's fine. If you would rather just undo your microphone and talk, that is fine too. Just if you do that, let me know who's talking, just because I want to know who's talking. It's not like I'm keeping count or anything. I just, it's just weird. All of a sudden I hear a voice. So it's better to actually hear a person or to actually know who I'm talking to. Let me do this. Okay, good. Okay, so Chapter 6, I'm going to kind of go over all the information, and then if you guys have questions on it, we can go over some questions, and then like I said, I will have some problems that we will do as well. Okay, so the first one is draw a Lewis structure using those 5 rules. All right, if you remember those rules, so remember the first rule is you have to figure out how many valence electrons it has. Then you got to do a skeletal structure where you've got a central atom and then all the atoms around it. And then you got to put on the electrons on the outer atoms. Any remaining you put on the center if you're not octet. Okay, so why don't we do a few Lewis structures. So let me pull up a Word document so I can write on this. I'll show you my new handy dandy tool that I got. So let's do, let me think of a pencil. What color shows up? Let's do black. Let me show you this. You just got to get used to it. Alright, so let's do S. Okay, so go ahead and draw. Actually, before we do that, let me, because I want to do everything. So, also tell me the geometries. You guys remember the electron group geometries as well as a molecular geometry? So let's kind of put those together as well as if there's a resonance structure. Okay, that's usually how I'll ask the question. I'll say, draw the structure. Are there any resonance structures? You don't have to show me what they are. You just have to tell me if there are any. And then also go through the electron group geometry, and then also tell me the molecular geometry. Remember, there was linear, trigonal, planar, and tetrahedral. And then you have all of the molecular geometries, which we have like bent and a pyramidal and things like that. Okay, so let's go back to this again. I know it deleted it, so we can get back again. Annotate. Just a new tool to get used to. I'll give you some time to do that. Actually close this and pull up. Okay, Kim. Thanks for letting me know. Okay, good. All right, so let's go through this. So, first the valence electrons. So, again, I'm trying to get used to this pen thing. I know on the videos I used it, but that was like a long time ago. You have to like kind of relearn. I don't know what this is. Fine. So the valence electrons. So sulfur is in the 6A. So there's 6 valence electrons for sulfur. And then each oxygen is also has 6 because it's in the 6A row. And then we have a -2 charge, so we're going to add another 2 electrons. So that gives me a total of 20 valence electrons. All right. And then we draw, the second is a skeletal structure, so sulfur's in the middle. Each oxygen is around it. Put the maximum electrons outside. All right. And then at this point, you want to quantitate how many electrons you have total and subtract it from the total amount, and any remainder you put on the central atom. All right, so I have 2 here, another 2 there, another 2 there, and remember each bond is 2 electrons. So around this oxygen, I've got 8 electrons. All right, and then this oxygen right here also has 2, 4, 6, 8. So I have 8 there. So I currently am using 16 of my 20 electrons. So that means I have 4 more electrons available. So those go as pairs on the central atom. So there's 2 of the 4, and then there's the other 4. All right. So that would be this. Okay, and then the last step is make sure everything is octet. All right. So the oxygen we already decided is octet, 2, 4, 6, 8. And then this oxygen right here is 8, 2, 4, 6, 8. And then the sulfur has 2 here and 2 down here, with 2 here and another 2 there, for a total of 8. So everything's octet. I also have accounted for all 20. So if you want to go back and check, that's a good thing. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So all 20 accounted for. Everything is octet, so that would be the structure of the molecule. Okay. As far as the electron group geometry, remember you have 3 choices. They're either tetrahedral, trigonal planar, or linear. All right. So what we had to do is we had to count how many electron groups are around our central atom. Okay. And remember, electron groups were either atoms or a lone pair. Lone pairs count as an electron group because they are electrons. So this sulfur has 1 lone pair here. It has a second lone pair here. So that's 2 groups. And then this oxygen is bonded, obviously, onto my sulfur. So that's a 3rd group. And then this oxygen is bonded for a total of 4 groups. So if you look, anything that has 4 groups is, for the electron group, is called tetrahedral. All right. We talked about that the bond angles were 109.5. I'm just kind of all going through everything. So even though I drew it as a linear molecule, remember, it doesn't really mean it's a linear molecule. Technically, this is how it should be written. I kind of showed you how to draw this tetrahedral with the wedge. You can put the oxygens here. And then I kind of showed you that if you want to put a bond for the electrons, you're more than welcome to do that, to kind of show a tetrahedral shape to it. So technically, that's really how to be. Now, if you drew this, that's totally fine. Unless I ask you otherwise, draw it in the correct geometry. But you have to make sure that you realize that this is the actual geometry. It's not where the oxygens are straight across. Okay? So then the molecular geometry. So remember that list I gave you guys? If you look tetrahedral, 2 atoms and 2 lone pairs. Do you guys remember what that shape is? If you want to type it in, go ahead and type it in. Bent. Very good, Kimberly. Yes. So there'll be a bent shape to it. All right. So if you did want to show that bent shape, but in a non-3D way, you can actually draw it like this. So any 3 of these structures, if you want to draw it like this and have the lone pairs like that, and the lone pairs here, and then you can have like the 2 lone pairs up here. So notice that really kind of shows a bent shape. Okay. So is that good? Everyone all right with that? I want to, let me think here for a second. Yeah, I think that's good. Okay. Questions, or we good? All right, good. All right, let's go back to our slide. Not our slides, our All right, the three exceptions, we talked about three exceptions were hydrogen is an exception, along with boron and nitrogen. We said that boron only is happy with only 6 electrons, where everything else was 8. Hydrogen only wants 2, and nitrogen is able to actually have an odd number. So we can actually have an odd number. We also talked about that sulfur and phosphorus have the expanded octet rule. So those can actually be more than 8. I'm really not going to test you too much on that. I don't know what kind of question I'm going to have. It'll be a multiple choice question. As long as you know general what everything has. I'm sorry, the exceptions. So I'm just looking at my notes real quick. Yeah, so it's boron has 6 valence electrons. Nitrogen is able to have an odd number. And then sulfur and phosphorus have the expanded shell rule. Okay, and then resonance, I guess I forgot to talk about resonance with this structure. So let me, for some reason I can't draw it just in this. I gotta go in slideshow. It's annoying, but it is what it is. Oh, that's not what I want. I'll have to figure this out more every time. Every day I'll figure more and more out. So we had the sulfur. We had our oxygen, and pairs up here. So is there resonance, guys? Type an N or a W. I'm sorry, or a Y. For yes, N for no. Yes, no, correct. This does not have resonance. Good. Yep, it does not have resonance. So remember, resonance, I would have to have a double bond here. So, like, for example, if my structure, let's just say, looked like this instead. Okay, because I have a double bond here next door to a single bond, that's when I would have resonance. Okay, so, okay, hold on one second, guys. Oh, here, why don't you grab a whole bunch? All right, sorry about that. Mom is doing the homeschooling today, so that's good. Okay, so that would have resonance. Remember, if you can draw a molecule, like the same molecule, differently, then you have a resonance structure. So these two, usually you draw this the double-headed arrow to actually show a resonance. It's not important, but that's basically how you know. So this would not, because I have all single bonds. Because everything is a single bond, I don't have resonance. Really, if you have a double bond or a triple bond, you would have a resonance structure. All right, good. And then there's also another question as if the molecule is polar or nonpolar. We talked about polarity, polar versus nonpolar. And we talked about how you have to add up all of the vectors. You guys remember that vector analysis thing? Where you have to look at the electronegativity of the atoms. All right, let me pull up a... yeah, let's put key. Yeah, good, okay. Let me pull up a periodic table real quick. That would be good to have under handouts, right? Okay, so remember electronegativity, which is also, let me go back to, remember on the review, no electronegativity, bond polarity, and molecular polarity. So off of this one structure, that's great. We're pretty much doing all of this. Okay, so electronegativity, remember, has to do with remember that fluorine has the highest electronegativity. Okay, so anything as you get closer to fluorine, that's the highest electronegativity. So remember, as we go this way, we increase in electronegativity. It gets higher, okay? And as we go up the periodic table, we also increase in electronegativity. Okay, so fluorine is the highest, and as we get closer to it, we increase. So oxygen would have a second electronegativity, chlorine too. Okay, now remember in class I talked about numbers. I said don't worry about the numbers. I know in the homework you do have to kind of worry about the numbers because they ask you things that are pretty close. On the exam, it'll be very obvious. I'll ask you in comparing carbon and chlorine. I mean, there it's an obvious. Chlorine has a much higher electronegativity than carbon would be, so it's much closer. But like asking things, so with oxygen and neon. So yeah, so that's a good question. Neon, the noble gases don't have electronegativities. And the reason is because they don't form bonds. An atom that forms a bond is when we look at electronegativities. Okay, so we don't have to worry about that. But pretty much oxygen and chlorine would have pretty much equal ones. If neon, well, no, let's not even answer that. So does that make sense? So on the noble gases, so electronegativity is really if two atoms are bonded onto each other. So you have to have A bonded onto B. So remember in class I talked about a tug of war. It's a tug of war between A and B. If B is a stronger group, obviously the electrons in the bond are going to be pulled towards B. So therefore B is higher electronegativity. Where did everything just go? Right. For some reason it closed on me. All right. I hear that somebody has their mic on. If you want to keep it on, that's fine. If you want to turn it off, I can find out who it is, but I hear some clicking. Okay. Well, does that keep happening? The A and B example would make a dipole-dipole. Well, okay, so Kimberly, when you say it, so that arrow is a dipole, but when you say dipole-dipole, that implies the intermolecular forces. That doesn't have anything to do with this. So I'm not sure if you're getting those two confused, the difference between a dipole arrow and a dipole-dipole intermolecular force. You do form a dipole-dipole intermolecular force with a polar molecule, but this I would not call a dipole-dipole. It's that arrow has a dipole to it. Does that make sense, Kimberly? Might be getting confused, but I'll get it. Okay. Okay. So yeah, so this arrow means that this molecule is polar, and you remember you have a partial. Why does that keep happening? That is annoying. Oh man. All right. Let me just use the mouse. It didn't happen with the mouse yesterday. I gotta use the pen. It's just maybe some pressing this button. Okay, so remember this had a partial negative, and this is a partial positive. So this arrow is a polar molecule. Okay, I'm sorry. This molecule is polar. This arrow is what's called a dipole arrow, meaning it's showing where the pole is going. What a dipole-dipole intermolecular force is this B is attracted towards another A on a molecule. Okay, so all these concepts are entwined in each other, but this arrow means it has a dipole, but a dipole-dipole intermolecular force is when this molecule is attracted towards another molecule. That's what the intermolecular force is. Okay, so hopefully that kind of clears it up. Okay, good. Okay. So I forgot what the concept I was talking about. So a partial negative and a partial positive. Okay, so fluorine has the higher electronegativity. I did tell you guys to make sure that you memorize that hydrogen and carbon are equal, approximately equal. Fun. All right. So, in going back to our example, let's go back to our example. Yeah, it's easier like to draw in this than it is with their application. Okay. So in order to figure out if a molecule is polar, so yes, these bonds are polar. Oxygen is more electronegative than sulfur. Remember, we showed that different ways, either with a dipole arrow, all right, so the arrow shows the direction of the pole, or we talked about that partial negative and partial positive. Okay. All right, so this oxygen is pulling this direction, and then this oxygen is pulling that direction. And remember, if we want to figure out if the molecule is polar, we have to add up these polarities. So, so in this case, imagine I have a particle. What is this? If I have a particle and I'm pulling it this way, and I'm pulling it that way at the same time, is this an additive effect, or do they cancel each other out? That's basically all that you want to look at. And they are adding to each other for an overall dipole of going that way. Okay, obviously if I had a particle going this way and the particle going that way, the equal amount, it's nonpolar, it cancels out. So since my molecule is a bent structure and the dipoles are pulling at angles, this does have an overall dipole, therefore the molecule is polar. So I have polar bonds. So you have polar bonds, and then you also have a polar molecule. Do the lone pairs and so they have a very, very small effect, much smaller than if you have it on a bond. So we kind of ignore them. All right, so that's a good question. It's very, very small. It like has a pole like this equivalent of an arrow. Right? Okay, good. Yep. Okay, so you're looking at both the polarity of the bonds. So these arrows is showing the polarity of the bonds. And then when you add up all of the arrows, you have the polarity of the molecule. And all you're basically looking for is as long as the arrows are not going equal and opposite ways. Okay, so like for example, carbon dioxide is a linear molecule. So you draw it like this. Okay. And I have a dipole arrow going this way because oxygen is more electronegative than carbon. Right? Oxygen is closer to fluorine. So I do have polar bonds. So I'll put like PB for polar bonds. All right. However, the molecule is nonpolar. So nonpolar molecule. Okay. So you can have polar bonds, but the molecule itself is nonpolar because, again, I'm looking at the sum of these arrows right here. So since it's linear, I'm pulling this way and that way at the equal amount, so therefore they cancel each other out, therefore it's nonpolar. So that's why when you do this, if I ask you, is the molecule polar or nonpolar, if you drew it like this, like that, you know, I had your lone pair here and a lone pair there or something, you'd say, oh, well, it's pulling this way and that way, so it cancels each other out, it's nonpolar. Okay, well, just because you drew it like that doesn't mean that's actually the shape. You have to make sure that you draw these in the correct geometries before you do this analysis. Okay, does that make sense? Also, a double bond has no more effect on a bond compared to a single bond because remember, this is resonance. What resonance is that double bond is actually being equally shared throughout our two oxygens. So that technically is what a resonance structure, or that is really what's going on. It's not like I have a double bond here, or I have a double bond over here. I have a partial double bond throughout my whole entire molecule. That's what's meant by resonance, that the electrons are resonating around our molecule.
So I have a question, Chris.
Yeah, Steve. Steve.
Oh, yeah, dude, it's my last professor.
I know. I got it. I understand.
Oh, wait, no, never mind. I got it.
Okay. Okay, good. Okay. Okay. Hey, Jacob. Okay. All right. Any other questions on that? So that pretty much, I think, summarizes quite a bit. I don't think I need to say this anymore.
Steve, Justin has a question.
Oh, yeah, sure.
So when we get a problem that's like SO2 minus, tell me if it's polar or non-polar. So do we have to go through and do all the steps for the Lewis structure, all the steps for the geometries, and then figure it out?
Yeah, so that's a good question. Pretty much you'll have to. That's the only way that you'll be able to tell if a molecule is polar or nonpolar, is that you have to know what the geometry is of the molecule. That's correct. That's exactly right. So even if the question doesn't say what's the structure, what's the geometry, it's kind of, you have to do that analysis in order to figure it out. So that's a very good question. So it's kind of like, as far as the hierarchy of how to do this. So like number one, the first thing that you always have to do, if I have any questions like that, is you first have to draw out a structure. All right, and then two, put it in the correct geometry. All right, and then once you get in the correct geometry, then you can go ahead and figure out if it's polar or nonpolar.
Got it.
Yeah, very good question. So you kind of have to do all this in order. So if you want to find this out, you have to do this and this. Okay? If you want to just find out a geometry, you have to do the structure and a geometry. It's not just like if I just give you like PO3 3 minus, there is no way that you should know, oh, this is going to be a polar molecule or something like that. You actually have to go ahead and draw it out. Okay? So, for practice, since I just come up with that, want to do all three of these things to it. I'll tell you what, you tell me, is this polar or nonpolar molecule? So we'll do that as a problem. I'm going to erase all this stuff on here. I got to find the eraser so that it doesn't get too... Oh, I saved that. I can't erase that. So resonance doesn't affect polarity. No, it doesn't. It's kind of its own thing. However, if you want to find out resonance, so as far as where it fits on the scale that I just gave you, resonance would be like you have to know the structure in order to figure out resonance. So we'll put here, I don't know, 2A if you want to find out resonance. All you need to know is there a double and a single bond on it? Okay. So why don't you just go ahead and find everything for this problem, just so you know. I actually like this. I feel like we'll just teach like this from now on. Let's not go to class, guys. Let's just meet online. We can all sleep in. We don't even have to shower. Just do whatever. Yeah, it'll help you, Kimberly, right? You just roll out of bed 5 minutes before and you're fine. Yeah. I have noticed that you've been on time the past 2 days, no problem. Just need a new slide. Yeah, then if you guys want to just put in there that you're done, that was actually really useful. In class, it's hard for me to tell when you guys are done, but if you just say done, then... Perfect, that's great. Okay, so, all right, good. Okay, so first thing, valence electron count. So number 1, phosphorus has 5 valence electrons. It's in the 5A row. Each oxygen has 6, and there's 3, so that's 18. And then a -3, we're going to add another 3. So that gives me 26 valence electrons. All right, so phosphorus then is the central atom. Remember, oxygen is never the central atom unless it has to be. We talked about 3 rules as to how you can tell if it's a central atom. And then we have our 3 oxygens. All right, and then with the maximum lone pairs around it. I'm going to draw lines just to save time. All right, so that's 24, 25, 26. So that's my 26 electrons. Everything is octet, so I don't have any pi bonds. So that's the structure. So we talked about you have to get the structure first. All right. Resonance, there is no resonance because I don't have a double bond. All right. So no resonance. And then, so the second thing now is the geometry. So there's 4 groups around my phosphorus. There's a lone pair as one of the groups. There is this oxygen, and this oxygen for 3 more groups. So a total of 4 groups. So therefore tetrahedral. Okay. And then number 3, I'm sorry, so a tetrahedral electron group geometry, but a molecular geometry of trigonal pyramidal. Trigonal pyramidal, or a pyramid. So technically it looks like, here's my phosphorus. Now this part of it you don't really have to do, but it might help to actually see how it looks. And then you can have your lone pair up here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay. Let's see, there's a question. Let me get my chat thing. Is it okay to just say pyramidal? Yeah, I'm fine with that. And so therefore we have oxygen is more electronegative than phosphorus, so we're going to have a pull going this way, a pull going that way, and a pull going that way. So you kind of have to think about this in your head. They're all kind of pulling down at an angle, so therefore would you say this is polar or non-polar? So once you put P for polar, put NP for non-polar. What do you guys think? Polar, yep. Okay, so Kimberly, you have a question mark. Is that because you are surprised that you got it correct, or because it was a guess? I wasn't confident. Okay. So if you have so here's the thing. Here's kind of a quick way to figure this out, and it always works. Okay, if you have a linear molecule, okay, or let's just do this. If you have the maximum number of groups around a central atom and they all have an equal pole, it's going to be nonpolar. Okay, so what does that mean? In order for this molecule, in order to be nonpolar, since it's tetrahedral, it would need 4 of the exact same groups around it in order to be nonpolar. So if my phosphorus had an oxygen here, an oxygen here, an oxygen here, and an oxygen back here, now it would be nonpolar. Okay, because I have a pull going up, a pull going down this way, a pull going down that way, and a pull going down that way. So imagine I have a particle that's being pulled this way, it's being pulled that way, it's being pulled that way, and it's being pulled that way. All right, these all cancel each other out at that point. So if you have a tetrahedral molecule and you have 4 of the exact same groups, it's going to be nonpolar. Otherwise, it's going to be polar. Okay, so there's really only one case where a molecule is nonpolar, is when it's all equal. If you have a trigonal planar molecule, but doesn't sulfur have less pull? The sulfur. So I was saying that if all of these no, that's not a sulfur. That's an oxygen. Sorry about that. I assume that's what you were talking about. Yeah, okay, good. But to answer your question, yes, you are correct. If this was a sulfur, since all 4 of them aren't exactly the same, then it would be nonpolar, because that sulfur is not going to pull as hard as the oxygens. Exactly. So it's kind of like, it's like all these arrows are much larger, all right? And then I have this small, if I did have a sulfur here, it's a smaller pole. So most of it cancels out, but a small amount won't. So yes, you are correct. It was supposed to be an oxygen. Okay, if you have 3 groups around your molecule, so if you have like a trigonal planar molecule, this is the geometry. Notice all 3 groups are equal, therefore it's nonpolar. Because I'm going to have a pole this way, a pole that way, and a pole that way. So it's like I have a particle, I'm pulling this way, and this way equally, therefore they all cancel each other out. Okay, but if I had, I don't know, a hydrogen here instead, then pretty much I would have a polar molecule. Okay, because that pole would not be there, because the boron and hydrogen are almost equal of each other, and our boron and fluorines are so much larger. Okay, the hydrogen has a tiny more than boron. Okay, so that rule always works. So if we have a tetrahedral with 3 atoms and 1 lone pair, it is not possible. That's correct. That's absolutely correct. Or if you have a molecule, let's say you have a phosphorus, like on our example, we had a sulfur with an oxygen, and 2 lone pairs. I know that this is going to be nonpolar because there are 4 groups around it. All 4 groups have to be the exact same atoms in order for it to be nonpolar. Since 2 of them are lone pairs and they don't matter, I know that the molecule is lone pair. Even though I didn't draw it in the correct geometry, this rule I'm giving you is a quick, easy way in order to determine if it's polar or nonpolar. I have, if I had an oxygen here and an oxygen here, then I know it's nonpolar. Okay. If the other bond with tetrahedral was a sulfur, would it be a polar? If the other bond, which molecule are you talking about, Kimberly? Are you talking about the sulfur one or the phosphorus one? Or the boron one? The other bond. Can you go on the microphone, Kimberly? It'd be easier that way. The Michael thought was a sulfur. Oh,
yeah, sorry. I don't know why I didn't think about doing
yeah,
that.
that's okay. So on this molecule here,
that one.
yeah,
Say that was S.
here, yeah.
Yeah, would that make the molecule polar then?
Yeah. So, like I was explaining on the molecule here. So, if I had oxygen, sometimes it does it. Oxygen, phosphorus. Yes, our sulfur is not as strong as the oxygen, so therefore it's slightly polar. Yes.
Okay.
Yep. And I mean, also, if I had, like a sulfur here and a sulfur here, it would also still be nonpolar. I'm sorry, polar. It would still be polar. It has to be all the exact same groups.
Got it.
Okay, so that might be an easy way in order to do it.
Yeah.
So, and a linear molecule is the same thing. If I have a linear molecule and all the groups are the same, it's polar. If I have an oxygen and a sulfur, then it's going to be, this is nonpolar. This is the same. If I have different groups, it's going to be polar because my carbon sulfur pole is not nearly as big as my carbon oxygen pole.
Got it.
Okay.
Yeah.
So
easy rule to
yes.
remember.
Yeah. So that should be an easy way to do it, and it always works. So it's not like you even need to do it in the correct geometries. If you just if you know that one rule, it should be easy to do. Okay, good. So I forgot what problem to do. Oh yeah, so it's this problem right here. So it would be polar because I got 3 groups pulling, but that 4th group is not pulling. Okay. If the molecule was this, let's say we figured out that the molecule looked like this instead, would that molecule be polar or nonpolar? You guys think? If you want to type in an N, non. Yep. Good, Jacob. That's exactly right. It'd be nonpolar because this is a trigonal planar molecule, so I should only have 3 groups around it, and all 3 groups are the exact same atom. Again, it doesn't matter if I have a double bond there, because remember, I equally have a double bond all throughout my whole entire molecule. So in reality, this is a trigonal planar molecule, so actually it would look like this. So if you took a particle, all right, and pulled it this way, we pulled it this way, and this way equally at the same time, your particle won't move. Okay? All right, good. Good job. Good review on that. I'm not going to save this. Chicken scratching. Okay, it's 11 o'clock. You guys want to take a quick break? Yeah, I want to take a quick break. I think we are. Let's see, what did we talk about? Just to go over these. The best for theory is, is the geometries. Is all the groups want to be as far away from each other as possible. Bond polarity, partial charges we talked about, and then the 3 intermolecular forces, how they affect boiling and melting. We'll talk about that when we come back from the break, and then we'll go over Chapter 7, which really is not a lot of stuff at all. Okay, so when we take a quick break, let's come back at 11:10 in 10 minutes. All right. I'm going to put myself on mute. Okay, there we go. Start the recording. Okay, intermolecular forces. Remember, there were 3 types of intermolecular forces. There was van der Waal forces, or London dispersion forces. I gave you all those names for it. I think your book calls it just dispersion forces. And then there's dipole forces, and there's hydrogen bonding. And then we talked about the weaker the bond. So if you have a dispersion force, they have lower boiling and melting points because the molecules are not held very tightly to each other. Where if you have hydrogen bonding, those molecules are much stronger, so the boiling points and the melting points are much higher on those. Okay? So any questions on intermolecular forces? And it's kind of an important concept. We talk about it in Chapter 7 a little bit. And then if there's any concept that you should remember after this class, that's probably like the one. Because it also helps with solubility. I think in Chapter 9 or 10, we talk about how you can look at a molecule and determine if it's going to be soluble in water or in nonpolar environments, just by all determining what type of intermolecular force it has. Things with hydrogen bond, they all dissolve other things with hydrogen bond. That's why sugar dissolves very well in water, because sugar has a lot of hydrogen bonding to it. It has a lot of OH groups, a lot of oxygens and hydrogens, and so does water. But if you take oil, which is just a bunch of carbons and hydrogens, very non-polar bonds, so they form a dispersion force, that does not dissolve in water. So water has hydrogen bonding, oil does not. It has a dispersion force, so that's why they do not mix. So can you give an example of the difference between dipole, and hydrogen bonding? Sure. So dipole, so hydrogen bonding is an example of dipole, except dipole does not have a hydrogen on it. That's basically the only difference. So let me get... Okay. So... Okay, so London dispersion is between nonpolar molecules. So like bromine. All right, if you have bromine molecule, this is nonpolar because you have 2 of the same atoms that are pulling each other. So because it's nonpolar, this force between the 2, or the attractive force between these 2, are very weak. All right. I think in the videos I talk about how this electron cloud that's around the atoms are kind of waving back and forth. It's kind of like water in a bucket, and if you shake the bucket, the water sloshes back and forth. So at one moment in time, the electrons are more on this bromine on the left. So on this bromine has more of the electron cloud and less on this bromine. So it makes this bromine slightly partial positive because its nucleus is more exposed because the electrons are being sloshed that way. Remember, our nucleus has a positive charge. So the nucleus is more exposed, therefore it has more of a partial positive, where this bromine now has more of the partial negative. So if you have another bromine that's right next to it, that's also kind of going that way, where more of the negative charge is on this bromine, and more of the positive charge is over here, you have this slight attractive force between this positively charged, partial positive bromine, to this partial negative bromine. All right, and then this negative is attracted towards another bromine that's a partial positive, and this is to a negative. But these charges are very small because it's not a polar bond. It's just at one moment these electrons are sloshing that way. Then at the next moment, these electrons slosh back that way, and you now have a partial negative on this bromine. So this interaction here breaks, and now this has to find a partial positive at another spot in order to be attracted to. So these forces are very weak. They are not a permanent force. It's kind of constantly all changing. So because of that, they're very weak bonds. Also, if we have like a carbon-hydrogen molecule, so remember we talked about carbon and hydrogen are equal in electronegativities. So carbon equals hydrogen in their electronegativity. Okay, so because of that, this is all nonpolar. All right, so this is going to form a dispersion force, or a London dispersion force, with another methane molecule. Okay, so a lot of people say, well, why is this not a hydrogen bond? Well, remember, for a hydrogen bond, you have to have two things. One, you have to have a polar hydrogen. All right, do we have a polar hydrogen here? No, we don't, because carbon and hydrogen make a non-polar bond. These are not polarized. All right, and then secondly, we obviously don't also have a lone pair. All right, and mostly hydrogen bonding happens between oxygen, nitrogen, and fluorine. It can also kind of happen on sulfur and other atoms, but these are the three main ones. So since my hydrogen is not attached onto one of these atoms, it can't be a hydrogen bond. So just because, so the saying is, a hydrogen bond is always with hydrogen, but if you have hydrogen, you don't always have a hydrogen bond. Okay, so just because it's hydrogen, don't assume it's hydrogen bond. You have to determine if this is a polar bond or not. Okay, so this molecule would have a dispersion force, or London force, because these are nonpolar. All right, so the second type of intermolecular force is a dipole dipole. I'm getting better at this pen thing. This is between a molecule that does have a polar bond, but it's not a hydrogen. Can't have a hydrogen. So like if we have a, let's say we have a fluorine attached to an iodine. Okay, fluorine is way more electronegative than iodine is. Like if you look on the periodic table, fluorine is the top. Remember we said fluorine is the most, and then underneath it, way down, is iodine. So this is a polar bond now. So London is nonpolar. Dipole dipole is polar. All right. So your fluorine always has a partial negative charge. Up here in this molecule, it's changing. It's changing between the bromines, what has the most negative and what has the most positive. Here it's not changing. It's a permanent dipole. So this fluorine is going to be attracted towards an iodine, because this iodine has a partial positive. And this iodine is going to be attracted towards another fluorine on a molecule. And these are much stronger because we constantly have this negative and positive charges. It's not all changing all back and forth. And then finally, the third one is hydrogen bonding. I'll just call it H bonding, which is a type of dipole because it has to be a polarized hydrogen. Let's just have a water molecule here. So it's polarized. Your hydrogen is partial positive. Your oxygen is partial negative. So you always have a polarized hydrogen. Right up here, it's not polar, so that's why it's a dispersion force. Here, it's polarized. Plus, remember I said it should be between. It's got to be bonded to an oxygen, nitrogen, or fluorine. So because the oxygen is partial negative, this is always going to be attracted towards a partial positive oxygen. So you see how it's kind of like a dipole dipole, where you have your oxygen is always negatively partial charge, and your hydrogen is always partial positive charge. So you'll always have that interaction. But in this case, it's even stronger because it's with a lone pair. Lone pairs make much stronger forces. So even though it is a type of dipole, Hydrogen bonding is a type of dipole, but it's so special, it's so important, it's so strong that it actually has its own name to it. So we don't call it dipole, we just call it hydrogen bonding. Okay, so hopefully that kind of answers those questions from Jordan and Jacob. Okay, if you're still confused, watch the videos on them, because I know, okay, good, all right, good, Jordan. Okay, so in order to figure out the type of force, the first thing you have to do is figure out which atoms are more electronegative. Then you have to figure out, are the bonds polar? So polar bonds or non-polar bonds. And then thirdly, once you have that, then you can go ahead and figure out, is it a London dispersion force, is it a dipole-dipole, or is it a hydrogen bond? So it kind of has to be in this order. First, you have to figure out, do you have a difference in electronegativity? Okay, so in this case, I do not, so therefore I know it's a non-polar bond. So it's going to be a dispersion. In this case, down here, I know these are not equal in electronegativity, therefore I'm going to have a polar bond. So then I got to figure out, is it a hydrogen bond or a dipole-dipole? Since I don't have a hydrogen, it's got to be a dipole-dipole. All right, good. Probably can actually delete these. That's all right. We'll just keep them. Okay, so that should finish up everything from chapter 6. Unless there's any other questions before we go to 7. Okay, good. Okay, chapter 7 really is not that hard. There aren't a lot of things with it. I think we spent half of a lecture period on all this information. Pretty much everything on the videos I talk about is everything that you need to know. So the first thing is I talk about the difference between solid, liquid, and gas. So it's looking at it at the atomic level. So I talked about that like for example, a solid has a fixed shape and a fixed volume. All right, and it has no compressibility. So those are the three things. So you should always know for each of them what the shape is, the volume, and if it's compressible or not. So if you think of a solid, it's already solid. It's compressed as far as it can be compressed. And what we're talking about compressibility is how far the atoms are from each other. In a solid, the atoms are all against each other, are pressed up against each other as much as possible. All right, and it has a fixed shape. So if you have a solid cube, it's the shape of the cube. It doesn't matter where it is; it'll always have the same shape. And its volume is its volume; it can't be changed. So fixed shape, fixed volume, non-compressible would be a solid. A liquid, however, is not as compressed as much. So you would say it's slightly compressed. It does have a fixed volume, so if you have 100 liters of it, you have 100 liters of it. It doesn't matter if it's in a glass, or if it's in a bowl, or if it's just on the floor. It's still 100 liters, so its volume is fixed. However, its shape is not fixed. Its shape is the shape of whatever container it's in. If it's in a glass, it's in the shape of the glass. If it's in a bowl, it's in the shape of the bowl. If it's on the ground, it's flat. It's in the shape of the ground. All right, and then finally, a gas really has no fixed shape or fixed volume. It takes on the shape and the volume of the container. If it's a small container, if it's a big container, if it's a rectangular, or if it's a balloon, it takes on its volume and shape of that. And then gas is very compressible because of the fact you have all that space in between all the atoms. So it is actually very compressible. So that's kind of how you have to understand it. All right, difference between amorphous and crystalline. Amorphous is where so this is talking about a crystal. So if you have, let's say you've got salt, which is sodium chloride. Salt could be crystallized very slowly, and all the atoms arrange themselves in a very uniform fashion. And usually those crystals are very clear. I'm sure everyone has seen a crystal of some sort where it looks really cool. It has a really cool shape to it, and it's clear, and it's just cool. That's implying that it was able to actually crystallize very slowly. The atoms were actually able to arrange themselves and pack on themselves very uniformly. Where amorphous is usually it's clouded, or it has a white, like in color. Like if you take salt, I mean, if you look at salt that we eat, it's a white color. That's because it wasn't allowed to actually crystallize very slowly. It actually crystallized very quickly, so it gives you this amorphous shape, meaning that the atoms are not arranged in a uniform fashion. But if you let salt crystallize very slowly, it has a crystalline shape to it. A good example that everyone might know is in sugar. If you just have regular sugar, it's usually white. It's not really crystalline, or in powdered sugar even. So that's amorphous. But if you look at sugar in the raw, if you guys have seen raw sugar in those packets, it's usually in like a brown little packet. Those have more of a crystalline shape to it. So that sugar was actually able to crystallize very slowly. Or if you look at rock candy, you guys ever seen rock candy? How it's crystallized in those cubes on a string or a stick of some sort. Pretty much how you make that is you take sugar, you put it in water, and boil it until it dissolves, and you put a lot of sugar inside that water. You super saturate that water, and then you put a stick inside the hot water, and you let the water slowly cool down. The slower it cools down, the more time those sugar molecules are able to actually pack and form on themselves. And it forms a very uniform structure at the atomic level, and it makes that really nice crystals in it. Where if you just take sugar and you quickly cool down that water, it just quickly crystallizes. It doesn't have time to actually form a crystalline shape to it. So it's more of a white color, and that's what we call a amorphous solid. Okay, so hopefully that shows the difference between amorphous and crystalline. Vapor pressure, viscosity, surface tension, volatility, and how the intermolecular forces affect them. We talked about that in class, but it's really on the videos. You don't have to know any more than what we talked about on the videos and in class, which is basically everything I talked about on the videos. Just kind of know what they mean, and just know how intermolecular forces affect them. So, like, for example, on viscosity, we talked about that there was two main things that you have to look at for viscosity. Number one is the strength of the intermolecular forces, right? And the other thing is the size of the molecule. So we talked about for something to have high viscosity, it's got to be a large molecule, and you have to have very strong intermolecular forces. So we talked about honey or syrup has pretty high viscosity, because it's these long chains of sugar molecules. So imagine one sugar molecule hooked to another sugar molecule, hooked to another one, hooked to another one, hooked to like billions and billions and billions of sugar molecules. That's one molecule, and it kind of entwines onto another molecule, so it kind of wraps up onto another molecule. And then you have a lot of hydrogen bonding, because sugar has a lot of OH groups to it, has a lot of hydrogen, oxygen on it. So it's kind of this shearing effect. So imagine you have these sugar molecules entwining each other, and it's being held on very tightly, so it can't really move, or it moves very slowly. So that would have high viscosity. But if you think about a molecule that has very weak intermolecular forces, but if it's still a long molecule, but the forces are very weak, they actually are able to slide very easily. So you have very low viscosity. Water also is another good example of this, where yes, you have very strong forces, but the molecule is very, very small. So it can't really all entangle onto itself. It's just small molecules that, yes, they're held on, but they're able to move across each other very easily. So that's kind of how you've got to understand all these things. Volatility, that's basically just based on how strong the forces are. So like water, for example, has very strong intermolecular forces, therefore it has very low volatility, where our gasoline is very volatile, so it means it evaporates very quickly. So because of the fact that it's very volatile, gasoline is just a hydrocarbon, it's just carbons and hydrogens. Carbons and hydrogens are nonpolar, is a nonpolar bond, so nonpolar molecule. So London, dispersion forces, so very weak forces, so it can evaporate very quickly. All right. The difference between evaporation and boiling, on the videos I talk about that. Evaporation happens on the surface of the molecule, where boiling happens within the molecule. So if you heat, here, when you increase heat to a molecule, do you decrease the yes, yeah, that could happen. We didn't talk about that, but yeah, increasing the heat, what it does is it causes all the molecules to actually vibrate a lot quicker. So in a way, you're kind of breaking some of those intermolecular forces. Remember, we talked about as you heat a molecule, in order to boil it, you are breaking those forces in between the molecules. And as soon as you break all the forces, that's when it turns into a gas. All right, so in the same thing here, as you heat honey or syrup, you are causing it to actually vibrate, and it's kind of expanding and contracting. So all these molecules are starting to unravel on themselves, as well as breaking all of those forces. So that's what's kind of happening at the atomic level. So yeah, that's a pretty that's an interesting question. All right, though we didn't talk about that, but yeah, I mean that's exactly right. As you heat it, and then obviously as you cool it, the opposite happens. As you cool honey, it gets really thick and very viscous, and it's the opposite effect. Our molecules aren't vibrating as much, so they're entwining on themselves even more and forming even more of those hydrogen bonds. All right, and then understanding energy and physical changes. So we talked about if you go from a solid, so imagine I have an ice cube, okay, and I want to turn it into a liquid. Are you adding heat to it, or are you removing heat? All right, you obviously have to add heat. If I have an ice cube and I want to melt it, I got to add heat to it. All right, so that's an endothermic process. I'm putting heat into it. All right, if I want to go from a liquid to a gas, so if I want to take liquid water and I want to boil it, what am I doing? I got to heat it up, right? I got to put it on the stove and heat it up. So again, I'm putting heat into it. Endothermic. You're putting heat into it. If you're doing the opposite, if you want to go from a liquid to a solid, what are you doing? All right. So in that case, you are taking a liquid and you're putting it in the freezer. What the freezer is doing is it's extracting the heat out of the object. So it's exothermic. I don't know if you guys have ever had an ice cube tray, and if you put really hot water in the ice cube tray, and if you put it in the freezer, you can obviously see all of the steam. It comes out, and it comes out a lot more in the cold environment. All right, that's because the cold environment is extracting out all that heat. Because remember, heat is transferred into a colder area. All right, I talked about that there's no such thing as a temperature. All right, or cold. There really is no such thing as cold. It's just that heat is being extracted into a colder environment. So if you hold a person's hand on a cold day and your hand is hot and the other person's hand is cold, it's really not the person's hand is cold. What's happening is the heat is being extracted from the hot hand into a cold hand. And we just call it cold, but what's really happening is the heat is transferring into a colder environment. Okay, and then specific heat, I talked about that. That's the amount of heat an object is able to absorb. So like metals, for example, absorb heat very easily. So like if you take a copper wire and if you put it on the stove, it absorbs heat very quickly. Water, on the other hand, has very low specific heat. Because it actually is able to actually absorb a lot of heat. All right, so that's kind of what specific heat is all about. I'm sorry. Metal has low specific heat. Water has very high specific heat, meaning it can absorb a lot of heat before it increases in a temperature. It takes a lot of heat in order to increase water. That's why water, you know how they say a watch pot never boils, because it takes so long in order to boil water. Where a piece of copper, if you put that on the stove, it'll heat up very, very quickly. Okay. All right. Other than that, I have nothing else. Do you guys have any questions? If you
No.
go, yep, go ahead.
I don't.
Oh, okay. All right, good. Good. Here's the exam 2 review sheet. So you guys can work on this. Just pull it up real quick. You also have all the answers there. Have I handed this out? I feel like I handed it out to you guys before you left. Or not. I don't know if I did. But you can see on the first part. Oh, also, guys, naming is still on this exam. So make sure you practice naming. Okay? So naming will be on this. So here's naming to structures, and here is structure into the name. Here's just a few problems, like converting grams into grams of chlorine. So notice we're starting with iron chloride, all right? But I'm asking you just about the chlorine. So that should hint to you have to use a mole-to-mole conversion in that case, all right? In this case, and the same thing, the number of grams of sodium in sodium bicarbonate. So you have to make sure that you know the structure of sodium bicarbonate, and then you do a mole-to-mole conversion. Empirical formula problems. Here I'm just asking you, are the molecules polar or nonpolar? So in this case, you have to be able to draw out the molecule. All right. Here's intermolecular forces, and I ask things circular. So in this case, I'm asking for all of the types of forces, and the strongest force is really the important one. Okay. I want to just make sure. Surface tension and viscosity, we just talked about that. Falling substances, the boiling points. And that looks like an empty page. All right. Good. Any other questions you guys have?
Nope.
Okay, good. So why don't we just call it a day. So tomorrow, basically how it's going to work is I'll open the room at 10 o'clock. If you guys, for you to come in and ask any questions. I might be in and out, so I'll still be here. I'll keep it open. If no one shows up after the first half hour, I'll close down the room. But if it's closed down and at 11 or something, I have a question, email me. I'll check my email and then I can open back up the room. Okay, so it's not a problem to have it open or not. We still technically have class. Yeah, there is an answer sheet. If you look right here, Exam 2 Review Answers. It's right there. It's right underneath it. All right, Michael?
Yeah. Say we're studying over the weekend,
Yep.
and Monday we have a question.
Yeah, so, okay, yep. That's a good question. If you think you can type it out, that's fine. If not, I have no problem in opening this up and talking to you. So have like a open office hour. I'm stuck indoors. It's not like I'm going anywhere. So yeah, I'm around, and if I'm able to do it, I'll say, if I'm busy with something, family stuff, I'll just say, yeah, are you able to meet like at 5 or something like that? So
Okay.
If that makes it easier, absolutely. Yep, I'm okay with that. All right, good. So I'm going to compile this video, and I'll post it in case you know someone who didn't make the class, or if you wanted to watch something else. All right, guys. Good seeing you. Maybe I'll see you guys tomorrow. Otherwise, have a good weekend. Study
Thanks,
hard.
Steve.
All right, bye.